welcome to AP Chemistry at Hund High School. I'm BBrown, and today we'll be looking at our last sections of Chapter 6. And first thing we'll look at is really electron configurations. And for many of you, this should be a review of many of the ideas that you learned in pre-AP chemistry. Electron configurations tell us how electrons are distributed among the different orbitals within an atom. And it's closely tied, and that's important information for understanding chemical activity. Now, the most stable configuration, or ground state, is that in which the electrons are in their lowest possible energy state. So that's an idea from Bohr, ground state idea. So you're most stable when the electrons are in their lowest energy level. And that's a core concept all the way through AP chemistry and in science. More stability is when you're at lower potential energy. So the lower potential energy is, the more stable the situation is. Now, when writing ground state electron configurations, we follow a few set of rules. One is Aufbau principle. Electrons fill orbitals in order of increasing energy with no more than 2 electrons per orbital. So we fill from lowest energy up, never putting more than 2 electrons in an orbital. So, and remember, the reason why is lowest energy maximizes attractions and minimizes repulsions. So it's really all about Coulomb's law, attractions and repulsions. So when you're at lowest energy, lowest potential energy, you're maximizing attractions and minimizing repulsions. Now, second fundamental principle with electron configurations is no 2 electrons can fill one orbital with the same spin. And this is Pauli exclusion principle. So the second electron in has to be different in some way, shape, or form. All 3 other quantum information is the same because it's in the same orbital. That must mean the spin must be different. And then the big one, Hund's rule, which hopefully by now you're familiar with, but we'll be looking at it more in depth. For degenerate orbitals, in other words, when we have more than 1 electron in, our orbitals are not at the same energy anymore within a level. Electrons, so we're talking about adding electrons into a sublevel, because the sublevels would be degenerate, and the energy level itself has split into various sublevels of different energy. So this applies when we're adding to a sublevel. P, D, or F sublevel in particular. Electrons fill each orbital singly before any orbital gets a second electron. And once again, it's all about minimizing repulsions, because when we put a second electron in the same region of space, that's going to increase the repulsions. So if we have 3 apartments on the P sublevel, we put 1 electron in each orbital before any of those orbitals get 2. And that's about minimizing repulsions. How do we show spin? Well, we've got quantum numbers, +1/2 and -1/2, but when we're drawing orbitals, it's just easiest to put an up arrow for the +1/2 spin and a down arrow for a -1/2 spin. So just use arrows. Now, when we're going to write or describe electron configurations, there's this thing called an Aufbau chart, which is one way to remember it, but really the best way to do this is have your periodic table blocked off. We've got the S block over here, and this is something that should be very familiar to you from pre-AP chemistry. So on the far left of our table, the first 2 columns on our periodic table make up the S block. And on the far right of the periodic table, boron through neon, so groups basically 3A through 8A or group 0, or groups 13 through 18 on the more modern method of numbering, just 1 through 18 across, you have the P block. And remember, helium doesn't really fit into that P block. It really fits over next to the hydrogen atom. So the electron that is going second into helium is actually filling its 1s orbital. And then the D block would be that middle part of the periodic table we call the transition metals. And then at the bottom of the periodic table we have our F block. And remember, you have an s orbital on each energy level, so it starts being numbered 1 on down to 7. The first energy level we have a P is 2, so we start numbering that 2 on down. The first time we see a D is the 3rd, so we start numbering that 3. And the first time we see an F is the 4th, so we start numbering that 4. And this then gives us, as we go through the periodic table, each atomic number on this form of the periodic table represents an electron position. So the 20th electron in any atom, which would be the last electron in the calcium atom, is actually going into a 4s orbital, and it's filling that orbital, because the 19th electron would be the first one in, and the 20th electron would be the second one in. So blocking off the periodic table in this way really helps us to see where the electrons are going. And remember, we have to add lowest energy first, and our apartment building gets kind of confusing because it's true that the 4s is actually lower in energy than the 3d. And that's exactly what this block periodic table shows. Electron 19 and 20 are going into the 4s, and then number 21 is going into the 3d. So after electron 18, over here at argon, which is in our last electron in our 3p sublevel, filling it up with 6, the 19th doesn't go to the 3d, it actually goes to the 4s. So this block periodic table set up in this way reminds us of exactly what comes next. And notice right in here what's happening. Between 56 and 71 there's a big blank. That's because these come next. So after we fill our 6s with the 56th electron, the 57th electron is going to go in the 4f. And we have to fill the whole 4f before we generally add to the 5th level d. So this periodic table really shows us all of the energy levels and how things go. Now, Hund's rule, I said we'd talk more about this briefly. For degenerate orbitals, that means a sublevel, the lowest energy is attained when the number of electrons with the same spin is maximized. In other words, we put one electron in each of these apartments. So the first electron in would go here, then the second electron in would go there, and then the third electron in would go there before any of these three equal energy orbitals gets a second electron. So that's what Hund's rule is you put one in your each orbital in your sublevel until it's filled, then you put your second one in. So thus electrons fill each orbital singly with their spins parallel before any orbital gets a second electron. By placing electrons in different orbitals, what you're really doing is minimizing electron-electron repulsion. The more repulsion you're going to get, the higher your energy is, and that's less stable. So we put electrons in each orbital by Hund's rule on that sublevel before any of them get a second. And that minimizes our electron-electron repulsion. Now each box in the diagram we were looking at represents an orbital. And our half arrows or full arrows, you can draw them either way, represent our electrons. And remember, the direction the arrow is pointing represents the spin. So we always put the positive 1/2 spin in first, so we put an up arrow in first when we're filling these. So lithium, which has 3 electrons, the first 2 electrons would fill the 1s, and that third electron would be an up arrow in that 2s orbital. Now, when we look at this picture, 4p5, that first number is actually telling us information, and so is the second number, and so is the third. So the different numbers are representing different information. Now at the beginning, we've got a number that represents the energy level. So if we write 4p5 in electron configuration, we mean on the 4th energy level, and then the p would represent our sublevel, that the orbital or orbital shape. So in this case, it's a p-shaped orbital, p sublevel, and then the superscript represents the number of electrons. So when we're writing electron configurations, we're trying to show the distribution of electrons in the atom, and this is a typical form we have of describing level and sublevel and how many electrons are in that sublevel. Now each sublevel with electrons is described with the number of electrons in the sublevel as a superscript. So when we're writing our normal electron configuration, which is listed down here. So this is usually what I mean when I say write the electron configuration. This right here is what we call an orbital diagram. So that is kind of overkill. It shows all of the quantum information. We've got every energy level, every sublevel shape, and each orientation of all of those sublevel shapes, and it also shows spin. So when we're writing what's called an orbital diagram or orbital notation, or like we see here for carbon, you're getting a ton of quantum information, and that's often too much information. So what we really do is we take this and we abbreviate it when we write our electron configuration notation. So we just describe every energy level that has electrons, every sublevel that has electrons, and how many are in that sublevel. So we have 2 electrons in the 1s, we have 2 electrons in the 2s, and in our 3 2p orbitals, that's a 2p sublevel, we have 2 electrons, so we write 2p2. So when we're writing what we call our normal electron configuration, we use numbers, letters, and superscripts to describe where the electrons are at. And remember, that's a simplified version of what we call an orbital diagram, which is this thing right here. Because orbital diagrams, when you have a lot of electrons, are very much a pain to draw. You have to list every single orbital. Now, Even regular electron configuration can be a pain when we have something like lead. So shorthand or noble gas configuration is a way we have abbreviating these. And I refer to it typically as noble gas abbreviation because it's very descriptive. Now, what we want to do is get rid of information that uh, doesn't have any effect in many chemical properties that we're looking at, and those would be our inside or inner level or core electrons. Really, the most important electrons to behavior are the electrons that are on the outside of the atom. Well, if you go back to your last noble gas, you're always guaranteeing you're talking about inner energy level information. So noble gas configuration is a way to basically stop talking about a whole bunch of electrons that are core and in the middle and we don't care about them, and just talk about what comes after that. So in the case of lead, if you go up and all the way over, the last noble gas we had before lead was xenon. And xenon is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6. Well, that's a mouthful. It's easier just to say all the electrons in xenon. So we use brackets and the last noble gas to represent those core electrons, and then we just describe the electrons that come after that. So if we're at xenon, looking at your periodic table, xenon is atomic number 54. So saying xenon in brackets describes those 54 electrons, and we just need to describe electrons 55 through 82 to describe lead then. And that's 6s2, 4f14, 5d10, 6p2. A much easier way of writing electron configurations. So we have orbital diagrams, electron configurations, and noble gas configurations. Now, there's a relationship between the periodic table then and what's going on with these electrons. We fill orbitals in order of increasing energy. That's by Aufbau. And therefore, when we get to our highest or outside energy level, we end up in very specific regions on the periodic table. Different blocks in the periodic table, which are shaded in the 4 different colors here, correspond to the different types of orbitals the last electrons are going into for those particular types of elements. Now, another thing to point out here is down the left side of most periodic tables, there are period numbers 1 through 7. The period actually represents which energy level. Everything in that row, the electrons in their highest energy level are going into whatever period you happen to be in. So if you know what period you're in on the periodic table, then you know what your highest energy level is, because that's going to represent N. Now the S and P blocks, the far left of the periodic table, the first 2 rows, and the last 6 rows on the right, represent elements where the last electron ends are going into S or P block. And those are always on highest levels. So if you remember from last year, the only valence electrons on the outside of an atom, are going to be in these 2 blocks. So these are particularly important elements on a periodic table. And they represent what are known as the representative or sometimes the main group elements. Usually we call them the representative elements. So the S and P block make up the representative elements because they represent the full continuum of chemical reactivity. Now the D block is our transition metals right here in the middle of the periodic table. And they represent groups 3 through 12, or 3b through 2b, depending on which numbering system you're using. And then finally our F block is the very bottom part. And remember, these are stacked in these 2 spots right here like a deck of cards. Well, you can only see the top card in the deck. So what they do is they pull them out and spread them across the bottom. And when we're in the F block, our inner transition metals, we're adding to the F sublevel. Now, you'll notice that this next discussion that we're going to have here is not in your notes, and that's because the AP test has now said anomalies to electron configurations aren't required to be known. But for freshman level chemistry, I guarantee they will get into electron configuration anomalies. So we're going to talk about it a little bit, but on the plus side, since my tests are designed to prepare you for the AP test, in any case where I really think that that's totally relevant, that means that you don't really have to memorize the anomalies, but I do want you to have a working understanding of them. So I want to talk about it, but that's why it's no longer in your notes. It's because these aren't questions I'm really going to be asking you about on my test, or you can expect to see on the AP test. But honestly, for freshman chemistry, it's something you should at least be familiar with. Some electron configurations appear to violate the rules that we've just talked about. And the reason why is, remember, it's all about stability. Electrons are going to exist where they are most stable, and that's about minimizing repulsions and getting to lower potential energy, because the lower potential energy, the more stable you are. So when we look at just a few anomalies that appear in the periodic table, it's usually not hard to figure out when we think about electron repulsion and other ideas why they're anomalies. So for instance, the electron configuration for chromium. Based on where it's at in the table, you would expect it to be different than 4s1 3d5. I mean, you'd expect it to be 4s2 3d4. That's what makes sense with what we've looked at based upon the Aufbau principle and so forth. So something different is going on here. So we would expect it to be 4s2 3d4, but it's not. It's actually 4s1 3d5. And based on experimental evidence, we know that to be true. So what's actually happening here? Why have we pulled an s orbital electron from our valence level and stuck it into an inner level 3D orbital? Well, think about the concept we talked about. The S and the D sublevels are close enough in energy. So they're actually fairly close in energy if you really look at the energy difference between our 4s and our 3D sublevels. That minimizing the electron repulsion can actually cause an unpaired situation to be lower in potential energy. So remember, putting that second electron in increases electron-electron repulsion. And these are close enough in energy that that little increase would actually put you above the 3D sublevel. So what really happens is it's more stable for it to exist as an unpaired lower electron repulsion, only one electron in that apartment, 4s, and then 5 unpaired 3ds. So it happens because 3D is close in energy to the 4s, and remember that second electron in the 4s is going to be higher in energy. So doing that is actually lower in overall potential energy, and that's why it happens. Now it also happens at the end of that sublevel as well. Copper is 4s1 3d10 rather than 4s2 3d9 for the same reason. It's actually a little bit lower in energy to pull that electron out and actually fill our entire 3D sublevel than to have it in that 4s sublevel. And once again, there's no electron repulsion advantage here, so we're looking at a slightly different situation because we've got the same number of paired electrons in both cases. But the S and D sublevels are really close in energy, and when you go from the 4s to the 3D, you're actually changing your distance from the nucleus. So you're close enough in energy that moving the electron closer to the nucleus, the 3D is closer to the nucleus than the 4s, is lowering potential energy. Stronger force of attraction, lowering the overall potential energy. I mean, that's why electrons add to the 1s orbital first in the first place. It is closer to the nucleus. By Coulomb's law, stronger force of attraction. It's more likely to exist there than farther away. So we're looking at the same kind of thing here. How come we go to 1s first rather than 2s? Well, it's because you're closer to the nucleus, lower potential energy. Same thing is actually true in this particular situation because the 3D, third energy level, closer to the nucleus than the fourth energy level is. So you can see these types of things being repeated multiple times in these two columns. Now, back to what you really do need to know for the AP test and my test. You need to also understand what's happening when we form ions, when we've messed with our ground state configuration and either added or removed electrons. And in particular, what we're really looking at here is when we remove electrons, we're making cations. Electrons are removed from the highest energy level first, the places that are farthest from the nucleus, because those have lower ionization energies. They're easier to move by Coulomb's law, distance kills attractive forces. The farther out you are, the easier it is to remove those electrons. So when you're looking at removing electrons from a metal, you're always going to remove from your valence level first. So sodium is 1s2, 2s2, 2p6, 3s1. When we make the sodium ion, we've lost an electron. Which one do we lose? Well, we yank it from the one that's farthest away from the nucleus because that's easiest to remove. So it becomes 1s2, 2s2, 2p6 as the sodium ion. If you look at tin, 5s2, 4d10, 5p2, and we are looking at removing 4 electrons from tin to make the stable tin 4+ ion, we have 4 electrons we have to remove. So notice we're removing the 5s2 and the 5p2 electrons. So we always remove from the valence level first. Now for transition metals, you first remove the highest p electrons and then the highest s electrons, and then you'd finally be pulling from the d's. Because transition metals can be multivalent, they can be stable multiple charge states, so they're a little bit different. So when you look at something like iron, which is 4s2 3d6, when we remove 2 electrons to make Fe2+, we remove the 4s electrons, and we end up with argon 3d6. Well, we can also form stable iron ions when removing 3 electrons. And that would end up giving us then argon 3d5. So remember, we would first pull from P's, then from S's on the highest level, and then finally we would pull from an inner level D, which is what we did here. Last idea before we finish up chapter 6 is the concept of diamagnetic and paramagnetic. Now your book talks about this in a different place, and now it's kind of the easy time to understand these two principles, so we're going to introduce the vocabulary idea here. Diamagnetic. Electrons are all paired, so the substance is not attracted to a magnetic field. So basically what's happening is when you're diamagnetic, you as an atom are not attracted to a magnetic field, because the way it works is some elements in the periodic table actually have a weak attraction to magnetic fields. Well, scientists couldn't explain why. Well, what they realized is things that were diamagnetic did not have this attraction to the magnetic field, always had every orbital which contained electrons with 2 electrons in it. In other words, they were all paired. There were no unpaired or single electron orbitals existing in that atom. Now, some substances do get attracted to a magnetic field, and they're known as paramagnetic. And the types of substances that did that were the types of substances that had unpaired electrons. And the more unpaired electrons you had, the greater your attraction to the magnetic field. So when something is diamagnetic versus paramagnetic, it's actually related to are orbitals all filled with 2, or are there some of them that only have 1 electron in them and therefore get attracted to a magnetic field? So is carbon paramagnetic? Would it be attracted to a magnetic field or not? Now, if we look at the orbital diagram, because here it's easier to see the pairing, that's what carbon would be. So yes, we have 2 orbitals, these 2 right here, that are partially filled. So that means this substance is going to be weakly attracted to a magnetic field. So yes, it is paramagnetic. And it would be more paramagnetic than a substance that only has 1 unpaired electron. Something like boron would only have 1 unpaired. So that would be paramagnetic, but not quite as strongly as carbon. And that's it. That finishes chapter 6.